Do you remember what flux is? Flux. 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 Okay, flux, that's flux. Flux is the amount of stuff that flows through a certain area. It's the amount of stuff that flows through a certain area. So we had the electric flux, and the electric flux was E dot dA. That was the definition of electric flux. And then Gauss's law showed us that the electric flux through a closed area, so flux is through any area, right? So you can have an area, you can have electric field through that area. This is just some arbitrary area and some arbitrary electric field. And you can calculate the amount of field lines that pass through the area A. Gauss's law specifically said the flux through a closed surface, so it can't be just an open area, it's got to be a closed surface, is dependent only on the charge enclosed by that surface. There's some parts of this that are very obvious, right? Because if the flux is the net number of field lines that pass through an area, and you don't have any charge inside of that area, right? So let's just take a cylinder, a closed cylinder, a can of Coke, and if you put some charges outside, those charges, let's say a single charge, has a field that looks like this, and it may be difficult to calculate the flux, but you can see that every field line that goes into the surface then leaves the surface. So the net flux is zero because there's no net flow either into or out of the surface. The only way that there is a net flow out of the surface is if the charge is inside the surface. Then there's a net flow out of the surface, right? So electric flux, Gauss's law said that the electric flux through a closed surface is equal to the charge enclosed divided by epsilon zero. And from that, we were able to calculate electric fields of charge distributions. So in the same way, we can talk about magnetic flux. Magnetic flux, big phi would give it a B now. So magnetic flux is simply going to be B dot dA. So the magnetic flux through any surface, if you've got some arbitrary area, and we got some arbitrary magnetic field, arbitrary magnetic field, B, and I didn't make it in purple, and that's A, then the flux through that surface is going to be B dot dA. But let's see what Gauss's law says for a closed surface. So for a closed surface, let's take our Coke can again, and let's put a magnetic field through that Coke can, or even, we could have a magnetic dipole, north-south. Whoops. The field lines go out from north and into south. I'm just making this kind of messy. Okay, I tried again. So let's say I have a dipole magnet, or any kind of magnet, and just notice that if it's outside of the can, all the field lines that go in come back out, right? So the only way that we can have flux through a closed surface is to put charge inside the surface. So what happens if I put a dipole inside the surface? Well, if I put a dipole inside the surface, right, again, we're talking about now, let's talk about the magnetic flux through a closed surface. So we're just applying Gauss's law. What is the magnetic flux through the closed surface? Let's just go ahead and see if we can guess, right? So just think about your field lines. They go from north to south, north to south. So north to south, north to south. Let me just draw one more field line. Whoops, that wasn't too symmetric, but okay. So there's my field lines. The magnet is the little red thing, and the Coke can is the bigger red thing, and then the field lines. So what is that net flux right there? Hopefully you have figured it out by now that is also zero. The net flux is zero because from that dipole, it's just like a dipole charge that even though it's enclosed in the surface, all the field lines that leave come back. So how is it that you can have a net flux of electric field through a surface and not a net flux of magnetic field? Or can you have a net flux of magnetic field, right? In electric field, what did we do? In electric field, for when we're talking about electric flux in Gauss's law, this is a separate picture. We said if we can enclose a net charge, so let's just have a Q, right? That net charge has a net flux through the surface. There's a net number of field lines leaving the surface. Didn't draw that very symmetric, but that's okay. But if I have an electric dipole, if I have a minus Q and a plus Q, then the field lines, what's the net flux through the surface? The net flux is zero because all the field lines that leave come back again. So the net flux here, the net electric flux, is through this closed surface is indeed zero. It's zero because the net charge enclosed is zero. But if I enclose a net charge not equal to zero, then Gauss's law says this equals the charge enclosed over epsilon zero. Okay, so now let's go back to the magnetic field. So how can I get a net magnetic flux? Well, the way we can get a net magnetic flux is to have a net magnetic charge inside the surface. How do we have a net magnetic charge? What does that mean? Well, what if we were to break, right, because there's not currently a net magnetic charge because there's both a north and a south. So what if we were to break this magnet in half, get rid of the south, and just keep the north? Then would we have a net magnetic charge? And the answer is no. Remember the discussion about the fact that you can't separate the north poles from the south poles. So that means you can never enclose a net magnetic charge. You can never enclose more norths than souths or more souths than norths. That would be a net magnetic charge. And that means that the flux through a closed surface for magnetic field, Gauss's law says that must always be zero. That is assuming that there are no monopoles. Oh, there's a lot of O's in that word. That there are no monopoles, that we cannot isolate a north pole from a south pole. If we can't isolate a north pole from the south pole, that means we can only have dipoles. That means that all field lines that go out must come back in. That means that Gauss's law for magnetism says that the net flux through a closed surface is zero. Again, that assumes no monopoles. If we ever discover monopoles, for sure, right, there's some questionable experiments out there, then this equation will change. But this is called Gauss's law for magnetism. I bring that up because it is just a good review of flux and dipoles and these concepts that we've been talking about all along. And also, this belongs in the list of equations, even though it really is just Gauss's law. But Gauss's law was originally for electricity, so we also have a Gauss's law for magnetism. So this belongs in our list of equations, right? So here, our list of equations. So in addition to those other equations that we now have as well, we have Gauss's law for magnetism, which says that B dot dA through a closed surface. Remember, this little circle here means closed surface. The flux through an open surface can be non-zero, but through a closed surface, it must equal zero. So this is Gauss's law for magnetism. And it is called Gauss's law for magnetism. So we're getting there with our collection of forces. Collection of electromagnetic descriptions of electromagnetic fields and electromagnetic charge. And we're getting there, and we're almost to the end where we're at Maxwell's equations.